Okay, let's get to it. Let's just start off by saying what these things mean. Okay. So the left-hand side, right, the limit of S of n is plus infinity, and goes to infinity. So yeah, what does that mean? Can somebody just tell me what the definition of that is? That's the same thing as saying, Ria, how about you? I'll pressure you. What does it mean the limit of the sequence is infinite, positive infinity?
Divergence.
Yes. Give me the we need
full sentence.
The full sentence, yeah. Grammatical.
Given any n greater than 0, there exists a big N such that if little n is greater than big N, S n is greater than 1.
Right. Okay. So given any height, right? Given any height, there's a corresponding time depending on that height, past which everybody is above that height. Okay. And then the other one is the one we're trying to show is that this is 0. So what's the definition of that? What's the definition of that? You're on a roll. Go ahead. Tell me what this means. The limit of this sequence being 0. Well,
Epsilon
yeah.
greater than 0.
Given any epsilon greater than 0.
There exists n such that n greater than n implies 1 over S n minus 0 greater than
Right? So here's the picture again. Given any set of bars around 0, right? There's a time dependent on epsilon such that past that time, everybody lies between the bars. Okay. So this is what we're given, right? This is what we have. This is what we want. Right? And you can sort of see what's going to happen, right? If somebody gives us an epsilon, right? How do we choose the time? How do we choose the time for it? Right? Somebody talk it out. How do you choose the time for it? Somebody gives you an epsilon. Okay, here it is. Epsilon is say 0.01. Okay. How do you choose the time past which everybody is within 0.01 of 0? How do you choose the time past which all these reciprocals are within 0.01 of 0? Are you all shy, or who knows how to do it and just doesn't want to say it? Raise your hand if you know how to do it. Close your eyes for a second. Okay, raise your finger if you know how to do it. Oh, okay. Okay, open your eyes. Okay, I thought you were all just being like recalcitrant. Like, I know what it is, but I'm not going to talk about it. But actually, it's not clear. Oh, okay. Okay. Right. What do we have? We have that we can make these guys as big as we want. Right? We can make the S of n's as big as we want. We want to make 1 over S of n as smaller than epsilon, right? Smaller than 0.01. Right? We can make S of n as big as we want. Right? And we want to make 1 over S of n smaller than 0.01. So, right? So, go ahead, Flo. What is it? So how do we how do we choose our time? Right? We can choose it. Like if we want S of n to be bigger than 100 million, there's a time past which that happens. Right? Mm-hmm. Or if S of n is bigger than 100 million, then 1 over S of n is
Can you make n equal 1 over epsilon?
Yeah.
Okay.
Yeah. That's it, exactly. Take your m, so So, right, given any m, there's a time past which we're bigger than that, right? So take our m to be 1 over epsilon. There's a time past which everybody is bigger than 1 over epsilon, right? If these guys are bigger than 1 over epsilon, then 1 over them is smaller than 1 over 1 over epsilon, namely epsilon. Right? And so that's it. Okay, so it's very simple. Yeah.
When you're if you were trying to prove that 1 over s of n minus, or 1 over s of n, the limit of that equals 0, would you choose an epsilon in terms of s of n, or would you?
So we are trying to show that the limit is 0.
Well, like if you were just given like prove that the limit of 1 over s of n equals 0,
Yeah.
you would choose epsilon in terms of big N or little n?
It's the other way around. The epsilon is not under your control. Somebody gives you an epsilon, and
You choose
then
n
you choose
in
the
terms
n.
of
Right?
big
You
N
want
or
to
epsilon.
show that you can choose the n.
Okay.
Right? So you say, okay. The idea is just as Mia said, right? We can make everybody bigger than 1 over epsilon. There's a time past which the s of n sequence exceeds 1 over epsilon, and so past that same time, the 1 over s of n sequence is going to be less than 1 over epsilon. Okay, so that's it. So you write it out. You say, okay, proof. Given any epsilon, so proof, fix epsilon, let m be 1 over epsilon. Right? Since the limit of s of n is positive infinity, there exists a time such that if we are past that time, s of n exceeds 1 over epsilon. But then 1 over s of n is less than epsilon. Right, and greater than 0. Right, so the distance of 1 over s of n minus 0 is smaller than epsilon. Right, and so you're done. And this n, of course, depends on the epsilon because you use the m being 1 over epsilon. Okay. Okay, so pretty simple, I hope. This. Where did people get stuck? Did anyone? What was hard? What was hard about this? Ichen, was anything hard about this?
It's like for all those kind of questions, it's just hard for me to come up with the n.
Hard to come up with the m. Okay.
To
Okay.
connect to.
Okay. Well, one way to do this is to, right, think about what you're trying to control and what you have control over. Right? We have control over this sort of thing. Right? This is the sort of thing that we can do. We can make Sn bigger than whatever m we like. Right? What we're trying to control, right? So we have control over this, and we want control over the distance of what we want this sort of control. This is the kind of control we want. But then you look at this and you say, well, this is the same thing. Right? This is the same thing as 1 over s of n being less than epsilon. In other words, s of n being greater than 1 over epsilon. Right? So if we want this thing to be bigger than 1 over epsilon, and we're allowed to make s of n bigger than anything, just make s of n bigger than 1 over epsilon. Right? So it actually should be pretty straightforward. You think about what you're trying to do and what you are able to do. Okay. Okay. Section 10, monotone sequences. Let's go on to the next section. Okay. So you've probably seen these sorts of things before. What are monotone sequences? Give me an example of a monotone sequence, or what does it mean to be a monotone sequence? Raleigh, it's boring. Ichen, go ahead.
Is it just like increasing or decreasing?
Yeah, increasing, decreasing, this sort of thing. So you define increasing sequences, you define non-decreasing sequences, you define decreasing sequences, and you define non-increasing sequences. Okay, so these are all sorts of sequences you've seen before. Right here, the next guy is strictly bigger, right? So it's actually increasing. For these guys, you say, well, you could be equal, right? You're allowed to be equal, but it's not allowed to get lower. So it's non-decreasing, right? Decreasing, of course, means that the next guy is smaller than you. Non-increasing means that the next guy might be equal to you, is either smaller or equal to you. Okay, so you have so I'm not going to write it up very cleanly, but you see what I mean. Okay. I should say that some people have different terminology for this. They'll call this one increasing, and this one strictly increasing. Okay, increasing, strictly increasing, decreasing, strictly decreasing. Okay, so just to keep that in mind, this one is sometimes called strictly increasing, strictly decreasing, and decreasing. Okay, and all of these guys are called monotonic sequences. So all these guys are called monotonic sequences. Okay, so if you have an increasing sequence, it's a monotonic sequence. If you're a monotonic sequence, you're one of these four types. Concept you've seen before. And the main thing for us is something called the monotonic sequence theorem. Monotonic sequence theorem. Who's heard of this before? No? Never heard of the monotonic sequence theorem? No? Okay. So what it says is the following, that suppose you have a monotonic sequence. Suppose you have a monotonic sequence, then the sequence converges implies that it is bounded. That's a lie. I'm lying to you. I'm lying to you. Why is it obvious that I'm lying to you? Why should you be saying, that's not the monotonic sequence theorem? That's clearly not any sort of theorem at all.
I didn't get it. What's BDT?
Bounded. Okay. Yeah, Ronnie.
Doesn't that have to be true for all kinds of
That's
sequences?
true for all sequences. That has nothing to do with monotonicity, right? If you're a convergent sequence, then you're bounded, right? We did this earlier, right? You do the game of you bound the tail, and then you choose, you look at the finite guys that are in the non-tail and bound those guys, right? So this part is actually true for everybody. Monotonic sequence theorem is this, that the reverse is true. If you're bounded, then you converge. And you see that that's not going to be true if your sequence is not monotonic, right? If your sequence is bouncing up and down, it would be bounded, right? Like oscillating between 1 and -1, it would be a bounded sequence, but would not converge, right? But what we're saying is that if it's monotonic and bounded, then it's going to converge. Okay, so let's think about why that will be true. Let's think about that. Why does that seem reasonable? What do people think is going to happen? You have a sequence, right? Let's pretend that it's a non-decreasing sequence. Okay. It could be, it's either from the increasing guys or the decreasing guys. Let's say that we're looking at one of the increasing guys. Okay. What's going to happen? Why does that have to converge? Right? So there's some bound on it. These guys are increasing. Why does that have to converge? And if it does converge, I mean, what is it going to converge to? You should have some sense of this. Mia, go ahead.
Is it because every term is either less than or equal to the term before it, so it can't be, it can only be getting closer and closer to a value, it can't get farther away from that value?
Okay. So there's some gigantic value, the even bigger m, and do we have to get close to that m?
No, like to the bound.
To the
'Cause
bound,
You can't,
okay.
you can't go higher than your bound, so
What-
you have to get closer and closer to your bound.
What's this bound? Is it
The limit?
the
The maximum of the.
the least upper bound, right? It'll be the least of these upper bounds, right? The smallest of these capital M's. Okay, right? So the least upper, what's going to happen? Yeah, that's right. The least upper bound is the fact that we have a bound above, right? The fact that we have a bound above by the least upper bound axiom will ensure that there's going to be a least upper bound, and then that least upper bound is going to be our limit. Okay, so that's the idea. You say, okay, S of n is bounded above, so has a least upper bound, right? So the set of values has a least upper bound. Okay. Call that thing m. Okay. And what we're going to say is that we claim that, in fact, the limit of S of n is that value. Okay, so what do we need to do to show that? We need to show that given any epsilon, there's a time past which everybody is in that epsilon neighborhood. Right? That's the definition. Given any epsilon, there exists a time such that if you're past that time, then S of n lies within n minus epsilon and plus epsilon. Okay, why does that happen? Why do we know that that's going to happen? Here is m, right? This m is the least upper bound. Right? M is the least upper bound of all the values. Of all the values. We take an epsilon. Given any epsilon, there's going to be a time past which everybody lies inside there. Fine.
You've proven that already.
We've proven that already. Okay. Can you make it? Can you tell me like what I should write here? I can't just say we've proven it already. Yeah.
Well, for example, that was kind of number on the midterm. What I did was I used the denseness of rationals theorem.
The density of rationals.
Yes. In order to prove that there will be infinitely many members of S7 within that interval.
It's not a density of rationals. You don't need to use density of rationals, but rather just say, look, here is m, and here's m minus epsilon. Right? And you know that your sequence, that this thing is the least upper bound, right? So remember, either m is one of your sequence, right? Let's throw that possibility out for right. Let's leave that one out. So let's say that just be careful. So given epsilon bigger than 0, we want to show that this is the time. Blah blah blah. Okay. Okay. So case 1. Suppose m is one of your values. Okay, suppose n is one of your values. Then what happens? Yeah, but
Then because it's a bound, the number can never go above it, so must mean that it'll just keep every number after that will always be.
that's right. That's right. In that case, then S of n equals m for all n bigger than n naught. Right? It's going to be constant from there on in, right? Because since m is S n naught is bigger than or equal to all sk for all k being an upper bound. And further, Sn is, we're saying that, again, we're assuming that it's increasing. So assume increasing. For all n bigger than n naught, Sn is going to be bigger than or equal to S sub n naught. Right? So they have to be equal. Right? So putting these two facts together shows that it's going to be constant from there on in. Right? Because this thing is the least upper bound, so it's going to be bigger than everybody, but it's going to be bigger than everybody past that time, but we also know that everybody past that time has to be bigger than it, right? Because it's an increasing sequence. Okay, so these two together tell you that Sn equals Sn naught for all n bigger than n naught. Okay, but in that case, it's obvious that the limit. In that case, we're done, right? So then the sequence converges. To that end. Okay. Case 2. Suppose that the least upper bound, m, is not one of the values. Okay. Well, we showed earlier that if the least upper bound is not contained in the set, then given any epsilon, there is at least one element in there. Right? One element of the set is going to be in there. Remember this? Right, because if there isn't anybody in there, then this is not the least upper bound, right? Then this would be an upper bound smaller than the actual, than the least upper bound contradiction. Okay.
All right, can you go over the entire
Go over the
entire proof, like case 1 and 2?
case 2. Yeah, I need to use this fact.
No, I'm asking, can we go over case 1 and 2 again?
Oh, I'm not done with case 2.
Okay, sure.
Do you want me to go over
Once
case?
you're done with it. Yeah. I don't quite follow, so.
You don't follow case 1, or you don't follow?
Yeah, I don't follow case 1.
Oh, okay. 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 I'll do case 2, and then I'll go over the whole thing again. Okay. Suppose the least upper bound is not one of the values. Suppose the least upper bound is not one of the values, then, as we saw before, there exists some Sn0 that lies inside of m minus epsilon m plus epsilon. Right? But then, since Sn is bigger than or equal to Sn naught for all n bigger than m naught, and Sn is less than m, right? Since m is the least upper bound of the Sn. And these guys are all bigger than n minus epsilon, right? Since that's true, we see that Sn lies in m minus epsilon, m plus epsilon for all n bigger than n naught. Okay, and that's what we're hoping for, right? Given an epsilon, we found a time past which everybody lies in the epsilon neighborhood of n. Yeah, Ray.
Why do we need to consider the interval between m and m plus epsilon? Is that just like formality?
Why do we need to consider m minus epsilon and plus epsilon?
No, m to m plus epsilon. Like, why do you have the m? Why isn't it m minus epsilon to m?
Yeah, it's true. You could just say that this.
That's just formality.
Yeah. Which, I mean, because it's just because of the definition, right? You want to show that S of n is inside here. We've actually done something better. We've shown that it lies in this smaller interval, the lower half of that interval. Yeah, it's true. Yeah. So I don't really need to say this part. It's obvious. Once we get this, then we're done. Yeah. Okay. So let me go over the cases again. Okay. So here's the picture. Okay. You have Sn, let's say it's non-decreasing. Okay. So you have this thing, right? Right. So, right, let m be the supremum of the Sns. So we've got the least upper bound, right? Okay, so here's m. These guys are increasing up to m. So case one is case one. Suppose at some point we hit that line. Okay, at some point we hit that line. So at time n naught, we actually hit m. But then after that point, because we're non-decreasing, we can't go any lower, and because this was an upper bound, we can't go any higher, right? So past that point, your sequence is constant, right? Right. That's what this is saying here, right? That this thing was an upper bound, so everybody's less than equal to it. But you have a non-decreasing sequence, so everybody is greater than equal to it. Right? Everybody is greater than equal to it. And so past that point, everybody must be equal to it. Well, then your sequence converges, and we're done. Okay. So that's the easy case. So suppose Sn equals m, then sequence S of n is eventually constant. It's going to be eventually constant. 2, suppose S of n, suppose m is never attained. Okay, suppose m is never attained. We get closer to it, but we never attain it. Okay. What we saw earlier was that if your least upper bound is not in your set, then given any interval n minus epsilon, there must be at least one element inside there. In fact, we saw that there had to be infinitely many elements inside there, right? But at least we know that there's one guy in there, and let's call that guy S of n naught. Okay, right? If there's nobody in there, then this wasn't the least upper bound contradiction, right? Okay, so we say, okay, well, there must be at least one guy. There must be at least one guy in there. Further, past that time, everybody is above Sn naught, right? So for n bigger than n naught, all the Sn's are going to be bigger than Sn naught, which is bigger than m minus epsilon, right? And all these guys are smaller than m, so we know that we found a time, right? We found a time n naught, and past that time, everybody lies in this interval here. And even stronger, it's even easier to say that they lie in this interval because they lie in this interval, right? So we've shown that, right? We've shown that past that time, everybody's in the epsilon neighborhood of m.
So it should be S sub n less than and not less than or equal to, right? Because that's what true of the
Here?
Yeah. No, the very last game on. Yeah.
Here?
Yeah.
Actually, because we said that m is never one of these guys, this is actually true.
So then why did you write less than or equal to?
That's also true. If it's less than or equal to, if it's less than, it's certainly less than or equal to. So it's sloppy. So this is maybe more true, but this was what was written there was also true.
Yeah, but okay. I think your less than or equal to contains less than, though less than doesn't contain less than or equal to. You know what I mean?
No. Look, these guys are all less than m.
Yeah, that is true. But
Yeah. So if they're all less than m, they're certainly less than or equal to m. Right? If everybody's less than m, then writing this is not incorrect. Right? And in any case, it doesn't matter because all we need is that everybody lies inside of this thing here. Yeah. So. Yeah, but you're right in saying that it's more accurate to say this. Okay. And further, if I didn't make that, then I shouldn't have said this. I should have said this. But it doesn't matter because all that matters is this last thing here, right? Okay. So monotonic sequence theorem, it's clear, right? Whenever you have a monotonic sequence, then it has to converge. It will converge to the least upper bound, or if it's decreasing, it'll converge to the greatest lower bound. Okay. Everyone all right? Any questions? Okay, now we're going to get to something very strange. Okay, so lim inf and lim sup. So these are sort of generalizations of the limit, very useful generalizations of the limit. Okay. So definition. Sn, a bounded sequence. The limit inferior, lim inf of Sn of the sequence Sn is defined like this. Lim inf of Sn is defined to be the limit as n goes to infinity of the collection of infimum maybe, of the S of n for n greater than n. So maybe I should put this as a bracket. No. Yeah, just leave it like that. Okay, so you have some sequence. So you have some sequence, and what you do is you look at the infimum, the greatest lower bound, past each time. So you say, at time 1, I'm going to look at the greatest lower bound of my set. Okay. That's going to be this guy here. Right. At time 2, I look at the greatest lower bound of my set. That's this guy here. Time 3, same. When I pass this point, I say, I'm going to look at the greatest lower bound of my set. Okay, the greatest lower bound of the remaining guys, right, of the tail. Okay, so greatest lower bound of the tail past n. Okay, and you take the limit as that n goes to infinity. Okay, you take the limit of those greatest lower bounds as n goes to infinity. That thing is called the lim inf. Okay, lim sup is of course defined with the sup. Similarly, this is true. Okay. Okay. So for example, if I have my sequence being, say, S of n is -1 to the n, so it's bouncing back. Yeah, well.
Sorry, if the sequence converges, does that mean that lim inf is equal to lim sup?
Yes, actually.
Okay.
Yes. Yeah, you'll see. Yeah. Okay. But the good thing about it is that even if the sequence doesn't converge, then you're still going to have a limit for lim sup. Okay. And it turns out that those can give you information. Those will give you information even if you don't have a limit. Okay. So for example, this sequence doesn't have a limit, right? But what's the lim inf going to be? -1, right? It's going to be -1, because you're going to look, right? You just look at the greatest lower bound of the tail, greatest lower bound of the tail. The greatest lower bound of the tail is always -1, right? As n goes to infinity, you just get -1. The lim sup is going to be 1. Okay, so just to get you thinking about it. So lim inf and lim sup always exist. It's always going to exist. And the reason is this. So let's think. Consider. Let A sub n be the inf of the tail past n. Okay, let B sub n be the be the sup of the tail past n. Okay, right, so that the lim inf is the limit of the A sub n's, the lim sup is the limit of the B sub n's. Okay, if that limit exists. Okay, now observe what happens to the A sub n's as time goes onwards, right? If I look at A sub n plus 1, what do I see about its relation to A sub n? Is it going to be bigger than A sub n? Smaller than A sub n?
Are we assuming that S sub n has a limit?
Nope. So I think we're taking the infimum over a tail, and then we're taking the infimum over a smaller tail. Right? If we're taking the infimum over a smaller tail, what's going to happen to the values? Suppose I take an infimum over a tiny set, I have an infimum over a huge set, and I take an infimum of a subset of that huge set. The infimum of the subset is going to be bigger, right? Because non-decreasing. Right? So we know that A sub n plus 1 is greater than or equal to A sub n, right? Because you're taking the infimum over a smaller set. You're taking an infimum over a subset of the original set. Okay. And similarly, B sub n plus 1 is going to be less than or equal to B sub n. And further, we know that A sub n is less than or equal to B sub n, right? Because it's the greatest lower bound and this is the least upper bound. Right? So putting that all together, A sub n is less than B sub n. B sub n. Oops, sorry. A sub n plus 1 is less than B sub n plus 1, which is less than B sub n. And this guy is greater than A sub n. Okay, so what do we see? We see that the A sub n's are increasing, a non-decreasing sequence. That the B sub n's are a non-increasing sequence. Right? And further, that they're bounded, right? The A sub n's, right, are all bounded by any, are all bounded by any of the B sub n's, right? And the B sub n's are bounded below by any of the A sub n's, right? And bounded, right? So both converge. And so that shows you that the limit of the infimums and the limit of the supremums is always going to exist. Okay. So you're guaranteed. Let me make one last remark, or maybe two. First is that if the limit of S sub n exists, it lies in this interval A sub n, B sub n. And then the second remark is that there's another way of defining this. There's a completely different way of defining this using subsequences, which we'll get to later. And I think that way is easier to understand. Okay. So that's it for today.